This video is going to focus on how you affect the rate of dissolving and why certain solutes dissolve in certain solvents. So to start with, let's talk about how can you make something dissolve faster in a solution to form a solution. So first thing we want to talk about is the size of the particles. If you increase the surface area, you're going to increase how fast the particles are able to dissolve. So for example, if I had granulated sugar and I had the same mass as a hard candy of sugar, the granulated sugar would dissolve faster in water, and that's because the granulated sugar has more surface area. More fresh portions of the solute will be exposed to the solvent, increasing how fast the solute can dissolve. Even though the sugar cube might look like more sugar, or you might think that, it's only the outside of that sugar cube is going to be brought into contact with the fresh portions of the solvent, so it's not going to dissolve as fast. Another factor is stirring, and you've seen this when you make iced tea in the summer. If you stir the iced tea, the sugar into the water, it will dissolve faster than if you didn't stir it. Temperature, so if a solution is hotter, if I increase the temperature, I can make the solute dissolve faster. And the last thing is the amount of solute you already have dissolved. If I have a lot of sugar already dissolved, it's going to be hard to get more sugar to dissolve into my solvent. So if there's less solute, it's easier to get more to dissolve. Remember last video we talked about solvation, which really has to do with the process of dissolving. Before we go forward and talk more about solvation, I really just want you to get the idea that when a compound is dissolving in water that's ionic, it's really being ripped apart into positive and negative ions. Since we have these ions that are in the aqueous phase, or the liquid phase, it's able to conduct electricity. When we talked about bonding, we talked about ionic compounds cannot conduct electricity as solids, but they can when they're liquid because their ions are free to move. So this idea of mobility of ions is important for being able to be an electrolyte, or something that's able to conduct electricity. So what is an electrolyte? Something that conducts electricity. And we should know that you can talk about being a better electrolyte or based on how concentrated the solution is. So we can compare different electrolytes and say which one is better. The one that has more ions, or is more concentrated, more ions, more solute per solvent in the solution, will be a better conductor of electricity. So all salts are electrolytes because they're all dissolved in some type of solution as long as they're in the aqueous phase. However, molecular compounds, or covalent molecules, do not break up into ions when we put them into water. They stay as themselves. They're not made up of a metal, non-metal, or a positive, negative ion. They're not going to dissociate into a positive, negative charge that are freely moving in solution. So since there are no charged ions that are able to move, freely moving ions, they will not conduct electricity. So ionic compounds can conduct due to the fact that they have these charged particles. The same idea goes back to when we talked about metallic bonding. We said you had to have mobile electrons, so this charge that's able to move to be able to carry the current. Here's a picture of an electrolyte versus a non-electrolyte. On the left-hand side, we have copper sulfate, an ionic compound, and we see that it's an electrolyte because when you have copper sulfate and water, the copper sulfate will break up into copper and sulfate ions in solution. Since they're mobile because they're in the aqueous phase, they'll be able to conduct electricity. There are mobile ions present. Whereas if you look at the right-hand side of this picture, we have C6H12O6, glucose in water. Glucose is covalent. Covalent molecules will not break up into ions. There'll be no mobile ions able to carry a charge, so it's a non-electrolyte. It does not conduct electricity. So how do we know, in general, when something will dissolve in something else? We use this saying, like dissolves like, and like dissolves like is based on polarity. So if you have a similar polarity, you will tend to dissolve in something that also has a similar polarity. So we could say that ionic and polar solutes tend to be more soluble in polar solvents. That's because ionic has that positive negative charge, and polar solutes have this oppositely end charge, partial positive, partial negative. So they tend to dissolve in something that also has a charged solvent. Non-polar solvents are more likely to dissolve in non-polar solutes, are more likely to dissolve in non-polar solvents. So that's where that like dissolves like. Non-polar, non-polar, polar dissolves in polar. The only thing that's a little bit different you have to memorize is ionic dissolves in polar, but you should think about the fact that ionic has a complete positive negative, and so similar to the polarity of a polar solvent, which is also partially positive, partial. And lastly, I just wanted to use two vocabulary words that we're going to be seeing moving forward: miscible and immiscible. Miscible is when you see two liquids that will dissolve in each other. So when you see sodium chloride dissolves in water, they are miscible. Immiscible is when two liquids do not dissolve in each other because they have different polarities. So this bottom picture we're going to look at is looks like magic sand, and we'll do a lab with this, where you see that the magic sand and water don't mix because they have different polarities. So we could say that they're immiscible. So when two things do dissolve, it's due to the fact that they have similar polarities. If you look at NaCl and water, NaCl is ionic solute, and water is a polar solvent, so that makes sense. Ionic does dissolve in polar solvents. So in general, nonpolar dissolves in nonpolar, polar dissolves in polar, and ionic solutes dissolve in polar solvents.